Now this particular system here is 40 petaflops, which is approximately the performance of the Sierra supercomputer in 2018. The Sierra supercomputer has 18,000 GPUs, Volta GPUs. This one node here replaces that entire supercomputer. 4,000 times increase in performance in 6 years. That is extreme Moore's law. Remember, I've said before that AI, NVIDIA has been scaling computing by about 1 million times every 10 years. And we're still on that track. And you heard me say before, the modern computer is an entire data center. The data center is a unit of computing. No longer just a PC, no longer just a server. The entire data center is running one job. And the operating system would change. The revolutionary computer called Hopper came into the world about 3 years ago. And it revolutionized AI as we know it. It became probably the most popular, most well-known computer in the world. In the last several years, we've been working on a new computer to make it possible for us to do inference time scaling, or basically thinking incredibly fast. Because when you think, you're generating a lot of tokens in your head, if you will. You're generating a lot of thoughts, and you iterate in your brain before you produce the answer. So what used to be one-shot AI is now going to be thinking AI, reasoning AI, inference time scaling AI. And that's going to take a lot more computation. And so we created a new system called Grace Blackwell. Grace Blackwell does several things. It has the ability to scale up. Scale up means to turn what is a computer into a giant computer. Scale out is to take a computer and connect many of them together and let the work be done in many different computers. Scaling out is easy. Scaling up is incredibly hard. Building larger computers that is beyond the limits of semiconductor physics is insanely hard. And that's what Grace Blackwell does. It's available in CoreWeave now for several weeks. It's already being used by many CSPs. And now you're starting to see it coming up from everywhere. Everybody's starting to tweet out that Grace Blackwell is in full production. In Q3 of this year, just as I promised, every single year, we will increase the performance of our platform every single year like rhythm. And this year, in Q3, we'll upgrade to Grace Blackwell GB300. Same architecture, same physical footprint, same electrical and mechanicals, but the chips inside have been upgraded. It has upgraded with a new Blackwell chip, is now 1.5 times more inference performance, has 1.5 times more HBM memory, and it has 2 times more networking. And so the overall system performance is higher. Well, let's take a look at what's inside Grace Blackwell. Grace Blackwell starts with this compute node. This compute node right here, this is one of the compute nodes. This is what the last generation looks like, the B200. This is what B300 looks like. Notice right here in the center, it's 100% liquid cooled now, but otherwise, externally, it's the same. You could plug it into the same systems and same chassis. And so this is the Grace Blackwell GB300 system. It's 1.5 times more inference performance. The training performance is about the same, but the inference performance is 1.5 times more. Remember, I've said before that AI, NVIDIA has been scaling computing by about 1 million times every 10 years. And we're still on that track. But the way to do that is not just to make the chips faster. There's only a limit to how fast you can make chips and how big you can make chips. In the case of Blackwell, we even connected 2 chips together to make it possible. TSMC worked with us to invent a new CoWoS process called CoWoS-L that made it possible for us to create these giant chips. But still, we want chips way bigger than that. And so we had to create what is called NVLink. This is the world's fastest switch. This NVLink here, right here, is 7.2 terabytes per second. 9 of these go into that rack. And those 9 switches are connected by this miracle. This is quite heavy. That's because I'm quite strong. I made I made it look so light, but this is 70 pounds. And so this is the NVLink spine. 2 miles of cables, 5,000 cables structured, all coaxed, impedance matched, and it connects all 72 GPUs to all of the other 72 GPUs across this network called NVLink switch. 130 terabytes per second of bandwidth across the NVLink spine. So just put in perspective, the peak traffic of the entire internet, is 900 terabits per second. Divide that by 8. This moves more traffic than the entire internet. One NVLink spine across this 9 of these NVLink switches, so that every single GPU can talk to every other GPU at exactly the same time. This is the miracle of GB200. And because there's a limit to how far you can drive SerDes, this is as far as any SerDes has ever driven. From chip, this goes chip to the switch, out to the spine, to any other switch, any other chip, all electrical. And so that limit caused us to put everything in one rack. And that one rack is 120 kilowatts, which is the reason why everything has to be liquid cooled. We now have the ability to disaggregate the GPUs out of one motherboard, essentially, across an entire rack. And so that entire rack is one motherboard. That's the miracle. Completely disaggregated, and now the GPU performance is incredible, the amount of memory is incredible, the networking bandwidth is incredible, and now we can really scale these out. Once we scale it up, then we can scale it out into large systems. And notice almost everything NVIDIA builds are gigantic. And the reason for that is because we're not building data centers and servers, we're building AI factories. This is CoreWeave, this is Oracle Cloud, and this is the XAI, Colossus factory. This is Stargate, 4 million square feet, 4 million square feet, 1 gigawatt. And so just think about this factory here. This 1 gigawatt factory is probably going to be about, 60 to 80 billion dollars. Out of that 60 to 80 billion dollars, the electronics, the computing part of it, these systems are 40, 50 billion dollars of it. And so these are gigantic factory investments. The reason why people build factories is because you know the answer. The more you buy, say it with me. The more you buy, the more you make. That's what factories do. Okay. And so today, we're announcing something very special. We're announcing NVIDIA NVLink Fusion. NVLink Fusion is so that you can build semi-custom AI infrastructure. Not just semi-custom chips, because those are the good old days. You want to build AI infrastructure. And everybody's AI infrastructure could be a little different. Some of you could have a lot more CPUs, and some of it could have a lot more NVIDIA GPUs, and some of it could be somebody's semi-custom ASICs. And those systems are so insanely hard to build. And they're all missing this one incredible ingredient. This incredible ingredient called NVLink. NVLink so that you could scale up these semi-custom systems and build really powerful computers. And so today we're announcing the NVLink Fusion. NVLink Fusion kind of works like this. This is the NVIDIA platform, 100% NVIDIA. You got NVIDIA CPU, NVIDIA GPU, the NVLink switches, the networking from NVIDIA called Spectrum-X or InfiniBand, NICs, network interconnects, switches, and all of the entire system, the entire infrastructure built end to end. And we now today make it possible for you to mix and match it even at the compute level. This would be what you would do using your custom ASIC. And it doesn't have to be just a transformer accelerator. It could be an accelerator of any kind that you would like to integrate into a large scale-up system. We create an NVLink chiplet. It's basically a switch that abuts right up to your chip. There's IP that will be available to integrate into your semi-custom ASIC. You've been building your own CPU for some time, and maybe your CPU has built a very large ecosystem, and you would like to integrate NVIDIA into your ecosystem. And now we make it possible for you to do that. You could do that by building your custom CPU. We provide you with our NVLink chip-to-chip interface into your ASIC. We connect it with NVLink chiplets, and now it connects and directly abuts into the Blackwell chips and our next generation Rubin chips. And again, it fits right into this ecosystem. This incredible body of work now becomes flexible and open for everybody to integrate into. You instantly get integrated into the entire larger NVIDIA ecosystem that makes it possible for you to scale up into these AI supercomputers. Now let me talk to you about some new product categories. As you know, I've shown you a couple of different computers. However, in order to serve the vast majority of the world, there are still some computers that are missing. And so I'm going to talk about them. This new computer we call DGX Spark is in full production. DGX Spark will be ready, will be available shortly, probably in a few weeks. We have tremendous partners working with us: Dell, HPI, ASUS, MSI, Gigabyte, Lenovo. Incredible partners working with us. And this is the DGX Spark. This is actually a production unit. This is our version. However, our partners are building a whole bunch of different versions. This is designed for AI native developers. If you're a developer, you're a student, you're a researcher, and you don't want to keep opening up the cloud and getting it prepared, and then when you're done scrubbing it, okay? But you would just like to have your own, basically your own AI cloud sitting right next to you, and it's always on, always waiting for you. It allows you to do your prototyping, early development, and this is what's amazing. This is DGX Spark. It's 1 petaflops and 128 gigabytes. In 2016, when I delivered DGX1, this is just the bezel. I can't lift the whole computer. It's 300 pounds. This is DGX1. This is 1 petaflops and 128 gigabytes. Of course, this is 128 gigabytes of HBM memory, and this is 128 gigabytes of LPDDR5X. The performance is, in fact, quite similar. But what's most important is that the work that you could work on this is the same work you could do here. It's an incredible achievement over just the course of about 10 years. Okay, so this is DGX Spark for anybody who would like to have their own AI supercomputer. If that one isn't big enough for you, here's one. This is another desk side. This is also going to be available from Dell and HPI, ASUS, Gigabyte, MSI, Lenovo. Amazing workstation companies. And this is going to be your own personal DGX supercomputer. This computer is the most performance you can possibly get out of a wall socket. You could put this in your kitchen, but just barely. If you put this in your kitchen and then somebody runs the microwave, I think that's the limit. And so this is the limit. This is the limit of what you can get out of a wall outlet. And this is a DGX station. The programming model of this and the giant systems that I showed you are the same. That's the amazing thing. One architecture, and this has the ability, enough capacity and performance to run a 1 trillion parameter AI model. Remember, Llama is Llama 70B. A 1 trillion parameter model is going to run wonderfully on this machine. Okay, so that's the DGX station. But in order for us to bring AI into a new world, and this new world is enterprise IT, we have to go back to our roots, and we have to reinvent computing and bring AI into traditional enterprise computing. And so let's take a look at that. Okay, this is the brand new RTX Pro Enterprise and Omniverse server. This server can run everything. Everything that runs in the world today should run here. Omniverse runs on here perfectly. But in addition to that, this is the computer for enterprise AI agents. Those AI agents could be only text. Those AI agents could also be computer graphics. It could be in video form. All of those workloads work on this system. No matter the modality, every single model that we know of in the world, every application that we know of should run on this. In fact, even Crysis works on here. Okay, so anybody who's a GeForce gamer? There are no GeForce gamer in the room. What connects these 8 GPUs, the new Blackwell RTX Pro 6000s, is this new motherboard. This new motherboard is actually a switched network. CX8 is a new category of chips. It's a switch first, networking chip second. It's also the most advanced networking chip in the world. So each one of these GPUs have their own networking interface. All of the GPUs are now communicating to all of the other GPUs on east-west traffic. Incredible performance. Okay, let's talk about robots. So agentic AIs, AI agents, a lot of different ways to say it, agents are essentially digital robots. The reason for that is because a robot perceives, understands, and plans. And that's essentially what agents do. But we would like to build also physical robots. And these physical robots, first, it starts with the ability to learn to be a robot. Now, you know that we've been working in autonomous systems for some time. Our self-driving car basically has 3 systems. There's the system for creating the AI model, and that's GB200, GB300. It's going to be used for that, training the AI model. Then you have Omniverse for simulating the AI model. And then when you're done with that AI model, you put that model, the AI, into the self-driving car. So we're doing exactly the same thing in robotic systems, just like cars. And so this is our Isaac GR00T platform. The simulation is exactly the same as Omniverse. The training system is the same. When you're done with the model, you put it inside this Isaac GR00T platform. And Isaac GR00T platform starts with a brand new computer called Jetson Thor. This is just started in production. It is an incredible processor. Basically, a robotic processor goes to self-driving cars, and it goes into a humanoid robotic system. On top is an operating system we call NVIDIA Isaac. The NVIDIA Isaac operating system is the runtime. It does all of the neural network processing, the sensor processing, pipelines all of it, and deliver actuated results. The biggest challenge in robotics is, the biggest challenge in AI overall is, what is your data strategy? And your data strategy has to be, that's where a great deal of research and a great deal of technology goes into. In the case of robotics, human demonstration, just like we demonstrate to our children or a coach demonstrates to an athlete, you demonstrate using teleoperations. You demonstrate to the robot how to perform the task, and the robot can generalize from that demonstration, because AI can generalize and we have technology for generalization. You can generalize from that one demonstration other techniques, okay? And so what if you want to teach this robot a whole bunch of skills? How many different teleoperation people do you need? Well, it turns out to be a lot. And so what we decided to do was use AI to amplify the human demonstration systems. And so this is essentially going from real to real and using an AI to help us expand, amplify the amount of data that was collected during human demonstration to train an AI model. Is that great? So in order for robotics to happen, you need AI. But in order to teach the AI, you need AI. And so this is really the great thing about the era of agents, where we need a large amount of synthetic data generation, robotics, a large amount of synthetic data generation, and skill learning called fine-tuning, which is a lot of reinforcement learning, and enormous amount of compute. And so this is a whole era where the training of these AI, the development of these AI, as well as the running of the AI needs an enormous amount of compute. Well, as I mentioned earlier, the world has a severe shortage of labor. And the reason why humanoid robotics is so important is because it is the only form of robot that can be deployed almost anywhere brownfield. It doesn't have to be greenfield. It could fit into the world we created. It could do the tasks that we made for ourselves. We engineered the world for ourselves, and now we could create a robot that fit into that world to help us. Now, the amazing thing about human robotics is not just the fact that if it worked, it could be quite versatile. It is likely the only robot that is likely to work. And the reason for that is because technology needs scale. Most of the robotic systems we've had so far are too low volume. And those low volume systems will never achieve the technology scale to get the flywheel going far enough, fast enough, so that we're willing to dedicate enough technology into it to make it better. But humanoid robot, it is likely to be the next multi-trillion-dollar industry. And the technology innovation is incredibly fast. And the consumption of computing and data centers, enormous. But this is one of those applications that needs 3 computers. One computer is an AI for learning. One computer is a simulation engine where the AI can learn how to be a robot in a virtual environment, and then also the deployment of it. Everything that moves will be robotic. As we put these robots into the factories, remember, the factories are also robotic. Today's factories are so incredibly complex. This is Delta's manufacturing line, and they're getting it ready for a robotic future. It is already robotics and software defined, and now in the future, there will be robots working in it. In order for us to create robots and design robots that operate as a fleet, as a team, working together in a factory that is also robotic, we have to give it Omniverse to learn how to work together. And that digital twin, you now have a digital twin of the robot, you have a digital twin of all of the equipment, you're gonna have digital twin of the factory. Those nested digital twins are gonna be part of what Omniverse is able to do. These are all digital twins. They're all simulations. They just look beautiful. The image just looks beautiful, but they're all digital twins. TSMC is building a digital twin of their next fab. As we speak, there are $5 trillion of plants being planned around the world. Over the next 3 years, $5 trillion of new plants. Because the world is reshaping, because reindustrialization moving around the world, new plants are being built everywhere. This is an enormous opportunity for us to make sure that they build it well and cost effectively and on time. And so putting everything into a digital twin is really a great first step and preparing it for a robotic future. In fact, building that $5 trillion doesn't include a new type of factory that we're building. And even our own factories, we put in a digital twin. This is the NVIDIA AI factory in a digital twin. Kaohsiung is a digital twin. They made Kaohsiung a digital twin. There are already hundreds of thousands of buildings, millions of miles of roads. And so, yes, Kaohsiung is a digital twin. We are at a once-in-a-lifetime opportunity. It is not an understatement to say that the opportunity ahead of us is extraordinary. For the very first time in all of our time together, not only are we creating the next generation of IT, we've done that several times. From PC to internet to cloud to mobile cloud, we've done that several times. But this time, not only are we creating the next generation of IT, we are in fact creating a whole new industry. This whole new industry is going to expose us to giant opportunities ahead. I look forward to partnering with all of you on building AI factories, agents for enterprises, robots, all of you amazing partners building the ecosystem with us around one architecture. And so I want to thank all of you for coming today. Have a great Computex, everybody. 大家谢谢。